Okay. All right, guys. Hi. So let's get started. We're following up on the design of the CMOS sequential circuits. Sorry, combinational circuits. Sorry, CMOS combinational circuits. So this is our like inverters, NAND gates, NOR gates, etc. So what we talked about in the previous lecture was how do we design a circuit that functions correctly, like an inverter that inverts and with a good noise margin. So we figured out, how we make the switching point by changing ratios of N and P devices given a certain current, etc. So today we're going to talk about, so now if you have a working circuit, um, does it work fast enough to meet your specifications? So we're going to be talking about the speed of operation of the devices. Now, first place, if you have a combinational circuit only, you have a combinational circuit only, speed will tell you, does it work fast enough? If your clock rate specifications, I don't know, the gigahertz, does it run that fast? If you have a sequential circuit, this timing issue would mean, does it work at all? Because what okay, sorry, my computer moved around. So that basically the question is, if you have, we'll talk about this a little bit later, but if you have, two, say, flip-flop or latch stages, is the data going to get from one point to another and meet setup times, for example? So speed is a very important part of trying to figure out how fast your circuit goes. Okay, and so we'll talk this lecture and the next lecture about ways to estimate the speed of your circuits, or whether the circuits meet timing requirements. And there's a real intimate relationship between speed and power. So after that, we'll talk about, what price you're paying for that speed and trying to minimize that. And so, the main things are that both of these are influenced. The important thing is that the speed and therefore power are influenced both by transistors themselves and by the connections between the transistors. So we'll also talk about the wires between the transistors. So these are the interconnections, well, they're the wires, okay, between the transistors. And these are, what we saw were metal 1, metal 2, metal 3, whatever layers used to connect the transistors are also important. Okay, I think we might have talked about this, but let me just give you guys a few definitions about the delay through a combinational circuit. So this is delay through combinational circuit. So for example, if you have an inverter, you give it a sort of a square wave input, what does it look like on the output? Okay, so we see that here. So this is more like a real waveform, input waveform. So this is the input. In this particular case, this is for a process where VDD is equal to 1 volt. Maybe, I think it might be for a 65 nanometer process. So on this axis, on the horizontal axis, we have time. On the vertical axis, we have the voltage. So the input is a square wave, but it has, you know, so you can see it's not a perfect square wave. It has a certain rise time, and even the rise time, it's got a couple of different subcomponents. Got this linear looking thing here, and then it's got this exponential slow conversion here, and then same thing with the fall time. There's a finite fall time and a fast linear transition, and then sort of an exponential thing. And then on this below chart, we have the output versus time. And you notice it's an inverted version of the input. So the input's going from low to high. So a little while, some time later after that, the output goes from high to low. And then when the input goes from high to low, the output goes from low to high a little bit later. So it's an inverter. Okay, so here are the definitions. We have something called the propagation delay, this TPDR, and it's different potentially for the rise and fall propagations. So that's the point at which the input transition is at its 50% point. The delay between that point and when the output gets to its 50% transition point is the falling, when it's a low to high going input, the output's going from a high to low. That's called the propagation delay falling. So it's from 50% point to 50% point, from the 50% of the input to 50% of the output. And then you have the same thing for the falling prop delay. So the input at 50% to the output at 50%. So that's I'm gonna reverse those. So that's a rising propagation delay, and the falling propagation delay is here. Okay, so it's referring, falling and rising refer to the output, falling or rising. Okay, and then you have a average propagation delay, which is the average of those two. Then the other thing you have in terms of a time performance is the actual rise and fall time of the output itself. And those are defined for us at the point from which we go to 0.8 times 0.8x the VDD to 0.2x the VDD, or the 80% to 20% point of the VDD. So that's the fall time or the rise time. Okay, and you know, really, some people also go to 1090, so 10% to 90%, but for our class, we'll be talking about 20% to 80% or 80% to 20% transitions for the fall and rise times. So those two things make up the delay in your circuit, the propagation delay and the rise and fall times. Okay. Now, there is something else. Usually, you know, when I first started learning about this stuff, always thought the propagation delay was the only important delay, and that's defined as the sort of the maximum delay between the input and the output. But the other important thing is something called the contamination delay, and that's the minimum input. So these are maximum delays. And these are minimum delays. From the input to the output. The reason you can get maximum and minimum is, for example, if you think about a CMOS NAND gate. And think about how the output, there's two ways for the output to rise. The output can rise there's three ways for the output to rise. Either A could be turned on, or B could be turned on, or both A and B can get turned on. And you'll see the specifics of this, but just from a common sense standpoint, you can see if the output is going from, say, 1, 1, so A and B, if that's transitioning to A, B being 0, 0, if that's the transition in time, that means both P MOSFETs turn on. So both of these guys turn on so that you get a fast, your delay is less than if you went from 1, 1 to only one of the P MOSFETs turned on. You just get less current coming to the output. So this is only one PMOS turning on. So by our definition, this would be this condition. So when you have this condition, when you might have a fast transition, this would be your contamination delay. And this would be your prop delay. And we'll see this in more detail. But basically the idea is as soon as, an inverter does not have such a thing as, there's no difference in an inverter between contamination and prop delay because there's only one way for there's only one input, one output. But as soon as you get to more complex gates, there are different ways to get the output to go from a 0 to a 1 or 1 to a 0, and you might have different delays through your circuit. The shortest delay will be called contamination delay. The longest delay is called a prop delay. Okay, so let's see. So, the most obvious way to calculate the delay through a circuit is you just simulate it, right? So simulation is, that's most obvious way to get delay. And that's typically done through a timing analyzer, okay? And what a timing analyzer does is it looks at, the arrival time of the inputs in a given block. Okay, and then it calculates the exit time of the outputs. What should I call it? I guess this is the arrival time of outputs. And conceptually, it's pretty simple. So these inputs, let's say these inputs are in this very small block, but this could be a very, very big block with tens of thousands of gates. You have these inputs, these 7 inputs, and each one the transition happens at a different time. That's called a different arrival times, and it depends on what's driving this from some external block is driving this guy, and depending on how fast that external block is, these inputs could arrive earlier or later. So for example, I0 and I3 through I6 are all arriving at time stamp 20, say, but then A2 is arriving much later, okay? And then each one of these combinational circuits like NAND, inverter, whatever, they have a certain delay associated with them, certain time delay. So for example, the output A7 of this NAND gate, it transitions at the later of the 2 inputs. So the transition will have to wait till I1 switches, which is at timestamp 30. It has a delay of 30. So this node A7 excuse me, transitions at timestamp 60, and then that gets a delay. And the output of this inverter is at timestamp 80, and then that 80, the other input of this NAND gate was directly connected to the input, but it has to wait till this guy gets there because this guy was already available at timestamp 50, and it's got a delay of 30. And anyway, the output transitions at timestamp 110. The output of the second half of this thing transitions at timestamp 140. And so you have this thing called, and so basically you have, this is what happens. So this is the delay, actual simulated delay. And then you have specified delay. You have a pretty complex digital circuit. So you're saying each block, whatever, has like a specified delay value. And the difference between these two, this delta in time, is called timing slack. Okay, so if you're doing this kind of thing where you're doing timing analysis, you'll hear timing slack a lot. And a positive slack means that the output switched, basically have more time compared to what you needed. So the output switched in time. So you have margin. And a negative slack means you ran out of time, means you're slower than you spec'd. Okay. So if you're in a situation where you have a positive timing slack when you do your timing analysis, you're good to go. You're done. So what, but if you have a negative slack, means you didn't make your timing specification. So for example, it could mean that you have a set of latches or flip-flops here and a set of flip-flops here. And if it took you too long, like longer than one clock cycle for the data to transition from one side to the other, means that you didn't allow enough time. So that means that if that happens, you basically have to go through a process of redesigning the circuit. Basically, you got trouble now, and you got to fix it. So that's typical use of a timing simulation tool for looking at the delay. But imagine, so you think, okay, I just need to simulate my circuits to figure out what the delay is. And that's, simulation is a good tool to look at the delay and a necessary tool, because it'll tell you the exact delay through a particular implementation. So you have this, you want to know what the delay across it is, and the simulation tool tells you that. But if you don't meet your timing, what the simulation tool won't do is tell you how to improve your circuit. It won't give you any information about that. Again, we're seeing this thing as, we got only 6 gates, and, it can kind of visually tell, etc. But usually you have a much more complicated scenario. So the simulation only tells you if a particular implementation of your circuit doesn't work or does work. But in the case where it doesn't work, it doesn't tell you how to get it to work. Okay, so for that, we need to find some way to better, get our timing estimation better than the simulation. Something that's faster than the simulation gives you a what if analysis. Okay, so let me add. Can I insert something here? Let's see, how do I do this? I'll add a page. and make it okay. So let's see what happens sort of in a typical timing optimization. So first thing is, let's say you have, a huge chip, right? Or a big block. When you do this timing analysis, the first thing you'll notice is that typically, unless you've really screwed up the design, most paths are okay or have positive slack because they're not critically fast. Their speed doesn't matter, just things come in and their output gets to where it needs to be quickly, or they're short enough. But then there's a few, usually, unless you're really screwed up, there are a few so-called critical paths. And besides the word slack, you'll keep hearing the word critical path when you're in a typical optimization, okay? And these are the paths that didn't meet timing. Oops. So they need optimization. Okay, so, and then how you got here. So, okay, so these are the critical paths. Now, if you have these critical paths in your design, if your simulation tool tells you that, you have a few different options to attack solving the problem. So, probably the best thing you can do is, so the first level of thing you can do is at the architectural level. Okay, so if you know the algorithm, oops. That you're trying to implement, you can do things like you can change the number of pipeline stages, say. Or size of the memory, say. So these are like, these are things at the architectural level of this particular block. So change the way you're achieving the functionality at the architectural level. Okay, so this is the biggest bang for your buck. This is the best thing you can do. But let's say that's not good enough, okay, for whatever reason. So the other option you have, so this is going from different levels of a hierarchy. So this is a high level in the hierarchy or abstraction, high level of abstraction to low level abstraction. So this is at the very, like a high level hierarchy. The next one is at the logic level. Okay, here you need to trade off in types of functional block. So for example, let's say you've got an adder in your circuit, you could decide, so examples would be like, should use a ripple carry adder or a look ahead carry adder, look ahead. Example, or another example is the number of gates between flip-flops or latches. So those kind of things, basically logic functions. The fan in, the number of fan in or fan out of your logic blocks, things like that. Okay, so that's at a lower level of abstraction logic than the architectural level. Okay, the third one is you could look at circuit level. Here you're looking at transistor sizing. You're actually like changing the design of your gates to have more drive, etc. And then the lowest level of abstraction is actually at the layout. Mostly this means, like floor planning, because, if you can change your floor plan, you can make a block physically closer to another block and reduce the delay of the wiring between the two blocks and try to get it to meet timing. Okay, so here in this class, or for the next few sections, we're mostly talking about these sections. So mostly we're talking about optimizing the logical functionality and the circuit level design to sort of optimize the timing. Okay, so that's what we're focused on. Okay, so, and to do that, we're looking at, if you want to optimize your circuit, the most fundamental way to do it is by doing, a transient response on your circuit. So what does that mean? So it means that, you got, again, the most fundamental level. Let's say you have an inverter. Driving another inverter. And you want to optimize this timing here. You can basically look at it as, let's see, you have a certain capacitance, certain resistance because of the wire. And this inverter supplies a certain amount of current. Okay, and you want to see a certain change in voltage out here. Okay, and that's really what's causing your delay in the CMOS circuit, is that you have these capacitances and you can only change the voltage across the capacitances. So delta V can't happen instantaneously. So you need current to charge capacitors. So you need the current is C dV dt. So to get your switching, you need a certain change in voltage. You have a bunch of capacitance, so you need to figure out, you need to put enough current to get it to happen fast enough. So again, at the most fundamental level, what you can do is you can write the equations. So write all the differential equations that define this change in voltage with respect to currents and calculate them. So that's kind of like something you can fundamentally do. Okay, so let's see, what does that look like? Let me copy this guy if I can. So let's look at a real simple case. Again, we have an inverter driving another inverter with a certain wire across it. Okay, so we know that there's some capacitors here, capacitances. So just the inverter stage driving it has, let me actually, so if I'm just going to draw this as if this first stage was going to drive a bunch of capacitors. So it has its own capacitances of diffusion. So there's a diffusion of the P-type transistor, there's a diffusion of the N-type transistor, of the load itself. Then there's the, I can just call it this capacitance of the wire. And then the gates of the device I'm driving, these gates also have a certain capacitance. So I can just draw them as capacitors. So these are gate capacitances. So I can basically lump all these capacitors into a single capacitor. They're all in parallel. So I can draw the circuit like this, and I can call all of them in total C load. So C load includes all of these capacitances. Okay, so basically we have this circuit. So then basically we have a transition on the input. So now we're doing a transient, like a fully, like if we were gonna do a differential circuits, etc., this is what we would do. So we would, put a step function on the input and see how the output changes. Okay, so let's do that. So our input, so our input is a step function. So that's, usually written as U and happens at t equal to t0. And we multiply that by VDD. So if I was going to have going to draw a graph of time versus voltage. And let's call this point VDD. My input would do this. All right, at time t equal to 0. That's the step function times the VDD value. Okay. So, and then at time, so less than that value, so if I look at my output out here somewhere, okay, before this point, because my input is 0, my output I know is going to be high. So that doesn't take a lot of analysis. So let me draw that in red. So let's see, the blue is input. Red is my output. Okay, so output is just VDD at less than T0. Okay, after that, so out here, oops. Oh, I like that. So out here, the change in V output depends on how much current you're discharging this capacitor with. So depending on this current IDSN, this thing will discharge in some way this guy. So it'll be a function of, and basically depends on the IDSN as a function of time over our capacitance C load. Okay, this basically, this current, simple enough, this current is discharging this capacitance. Now the trouble starts here, which is that IDSN actually, as we saw, changes on whether, for example, let's say in the pull down node, we're just looking at the NMOS, IDSN changes depending on what state this device is in. Okay, so first, let's say when t is less than t0, so out here, this gate is at 0, so that means there's no current. So IDSN is 0 out here. Okay, we're not pulling that node down. The capacitor stays at VDD. When we turn on the device, initially the output, where the output is sitting here, and as long as that output is greater than VDD minus VT, okay, let's write it in terms of what the device sees. The output here is the drain source of the NMOS is greater than the gate source of the NMOS minus VT. Okay, the gate source, the gate is VDD, that's the input, minus VT. So here, when V output is greater than VDD minus a VT, so if I was going to draw it here, okay, if that's happening, I'm in saturation. So my IDS current is going to be beta over 2 VDD minus VT squared. Okay, so what does that look like? Let me draw that over here. So that looks like a current source that's discharging the capacitor. Okay, the reason this is the reason it's a current source is, notice it's just a set current, doesn't depend on this VDD value, it's just pulling current out, okay? And so in that case, when we have this kind of equation, the delta V is just this current I, or IDSN, over the C. Okay, so means that here I just get sort of a linear type of drop. Okay, now let's see what happens after that point. So when VDD then, when VDSN, when the output, in this case, drops below VGS minus VT, the NMOS goes into linear operation. So basically the current IDSN changes to beta VDD minus VT minus V output over 2 times V output. Okay, so I'm just writing the level 1 equations for the currents. And in this case, what the circuit looks like is kind of it's not a great resistor because it's, sort of a non-linear resistor, but I don't know how to it's a nonlinear resistor, but a resistor nonetheless. So here, in this kind of function, the delta V out looks like it's proportional. So this is a proportionality, proportional to sort of an exponential response. Okay, so once I get below this point, once this happens, I will get an exponential sort of drop. Okay, so that's what it'll look like from the input to the output. Okay, so a pretty complicated type of function. And the problem is this part is pretty simple. You know, this part's pretty simple. The problem is that this current is changing on us as this transistor is changing its bias conditions. Okay, so it gives us this complicated curve. Okay. So, you know, if we try to solve, so let's just say we say, look, this is too hard to solve these equations by hand. You know, I've got all these different transistors, and again, imagine if I had more than this inverter. I had like a bunch of different devices here. I had, you know, a 3-input NAND gate. It was driving a complicated load, something like that. So let's say we just say that's too hard. I'm going to just use simulation. Okay. The problem again, if you use simulation, although it uses accurate models, as we saw, like these first level models aren't terribly accurate. Right? These are the first level ones. We had all sort of second order effects, especially at the finer geometries. So maybe it makes sense to simulate. But the problem with simulation is that, you know, you'll get something, but it doesn't tell you how to optimize that value. Let's say it's not what you want. Let's say, you know, that it's not a symmetric type of, like, let's say you have a very big difference between your the prop delay of your fall and prop delay of your rise, and that's going to screw things up. Question is how the simulation doesn't tell you how to improve on it, so you'll get stuck in a cycle if you're just simulating it, where you're changing the parameters in your simulation, resimulating, changing parameter, resimulating, etc. But the problem is there's usually too many degrees of freedom in a real circuit. Okay, you have too many things you can change at the same time, and you'll just keep chasing your tail, changing parameters and resimulating. So, and that's a mistake that, you know, typically gets done by, you know, you see a lot of young designers doing that, where they're not doing any analysis and they're just simulating, changing a parameter, simulating again. I do it sometimes too. You sort of get stuck in this loop. So, but it's not easy to see how you can change things. So, fully differential equation solving that was too cumbersome. And we were even with the cumbersomeness of it, we were using these inaccurate current voltage models. Whoops, shouldn't have done that. So that was the problem with that, fully differential equations. And simulation doesn't give you a lot of insight. So where does that leave us? That leaves us with the approach of trying to come up with some simpler models than this really complicated. The problem is really this current changing on us. So try to come up with a simpler model for a transistor that allows us to do sort of simple hand calculations. So how do we, you know, what does that look like? Well, so this curve here is a transition, falling transition for just a simple RC circuit. So this would be if I had a voltage and an R and a C. It would look like this basically. Okay, it's got this exponential drop. And if I was going to draw again qualitatively, if I was going to draw sort of this thing qualitatively, it would look like probably something like that. Oops. Let me just draw a little bit better. Remember, we had sort of a linear section and then an exponential section. So what we're going to say is that this thing is pretty close to this thing for doing hand calculations. Okay, just for doing hand estimations. Okay, we'll see in the book, it'll talk about, under typical conditions, the difference between these two curves ends up being, surprisingly low. Not at any particular time, but if you look at the total delay time, if you use, a simple RC model so basically you're saying I'm going to use this instead of this. That delta is only for the full prop delay. Is the difference is maybe around 7 to 10% in value for the overall propagation delay. At any one point, you could be pretty far off the mark, okay? But in terms of when the things sort of get to where they need to go, say the 50% point, et cetera, it's, pretty close, depending on which values you pick for the R and the C. Okay, so to make it easier to do an analysis. So what we'd like to do is use a effective resistance such that the prop delay ends up being just RC. Okay, and we can use this simple model. So the equation for this thing, so the equation for that, the transfer function, the S domain is 1 over 1 plus SRC. And so the output is VDD. If this is Vn is step function of VDD times exponential minus t over tau, where tau is RC. Okay. With all that, if we use that as the symbol for the prop delay, oops. If we wanted to use this for the prop delay, the prop delay would end up being this value. RC natural log of 2, which is the 50% point. Of this exponential transition. It's the 50% point. Okay. So now, it's natural log of 2. So this natural log of 2 is something like, I think it's something like 0.67 or something. But it's okay because we can actually wrap everything into this R effective. So this R effective is going to include, so it'd be the average resistance, or let's say it's determined by the average current output of the device. Of average current output, plus we'll put this factor of 0.67, which is this natural log of 2. Throw it in there, and that all becomes R effective. So that we can just say the prop delay is RC. Okay. So let me jump here and then we'll go back. So, okay, what are we doing here? Okay, so we're saying that instead of an NMOS transistor, well, actually I've got it drawn here. So let's say we have an NMOS transistor and it has a certain width of K. So this width is K times the minimum device. Okay. So let's say we just have a minimum for the sake of discussion, because I think sometimes this K factor throws people for a loop. So let's say you have a minimum size N MOSFET. And that minimum size is determined by the process. I think that our design rule said minimum width was 4 lambda, minimum length was 2 lambda or something, the lambda rules. If you have the minimum device, you can just say it's like a resistor of value R equivalent. It'll have a capacitance for the source. Okay, this node, this diffusion will have a certain capacitance. It's, let me move this so I'll give myself some room here. So it'll need a switch to turn on and off. Do that. Let me redraw this thing. It's drawn so badly. So we have the resistor, equivalent resistor. Then there'll be a switch. Then you'll have the diffusion current of the source. And that's the source connection. And then on the output, it has the diffusion current of the drain. And then on the input, whatever is driving it, the gate will have a certain capacitance. So this is capacitance of the gate. Okay, so when this N MOSFET is on, the switch closes, and it'll look like it just has a certain RC driving capability with a certain equivalent resistance. And a certain equivalent resistance, as we'll see, depends on the process. So for example, and we'll see how you're gonna get this later, for the 0.18 micron TSMC process that we're gonna do our projects on, our equivalent for an NMOS transistor is 2.6 kilo ohms per micron of width. So for a minimum transistor, yeah, per micron of width. Sorry. And then the C diffusion for N is, down here, diffusion N is 112 femtofarads. You guys don't need to write this down. It's all in the book. I'll tell you guys what table it's in. C Gate is 1.67 femtofarad per micron. Okay, and these are all on table 8.5 of the book on page 312. Okay, and then if you have, what this K factor means is, let's say if you have a device that's not a micron wide, right? If you want to make it 10 microns wide, you would end up having R divided by 10. So this is 2.6 kilo ohm. Sorry, this is times micron, not per micron. Okay, so if you made this 10 times wider, or 10 microns, you'll end up with 260 ohms. Okay, so basically you have this dividing factor. If this was K wider than your minimum size, you would have K times less resistance. But you would have K times more capacitance on the source and drain and the gate. Okay, this K factor really confuses everybody the first time they see it. Do you guys have any questions about that? Does it make sense? So remember that the I sub D is proportional to beta, and beta is proportional to width over length. Okay, so this resistor value is trying to emulate the average current for both linear and saturation currents. The current's linearly proportional on the width and inversely proportional on the length. We said in digital design, we're going to keep the length the same at the minimum size. And so basically, the wider we make a transistor, the more current it'll have, so the less resistance it'll have compared to a smaller device. So we have our base unit device that's going to have a certain R equivalent, and we look at every other device, every other NMOS that has a different width compared to that base device or our smallest device. It has a ratio, the ratio of W times less resistance than comparing the W of the base device. Does that make sense? Any questions?
Nope.
Okay. So you'll see how that works out. And the same thing we do for a P device. Okay. It's very similar, except, like I mentioned a while back, the P device, the mobility of holes are typically less than mobility of electrons. That means that we would expect the resistance of the P device to be greater than the resistance of the N device, okay, for the same size. And in fact, if you go to that same table, so table 8.5, same thing, you'll see that the equivalent resistance of a P device is 6.51 kilo ohm microns, or it's about 2, and so R sub P is about 2.5 times R sub N. Okay, so what we're just going to say is that just for the estimation again, is we're just going to say R sub P is 2 times R sub N. So in our specific case, it's a little bit worse than that, but this is going to be sort of easier to analyze if we just keep track of a single R value. Okay, so basically our minimum size P will have 2 times the resistance if it's the same size N, 2 times the resistance divided by, if you make it wider, by the width. So you can double the width and get, so if you have a PMOS that's double the width of an NMOS, it'll have the same resistance as the NMOS, okay? But it'll also have more capacitance because of these K factors. Okay, what else do I want to say? So this is some range of values. Again, these are all, you'll see if you look at table 8.5, it's comparing a bunch of processes, and you'll see how these capacitances, this is like very rough. It's approximately. But for this sake of our simple analysis, we're going to say all these capacitances are going to be the same. And they're all going to equal to something we call just C. Okay? But the actual value is going to change depending on the process. Again, you'll see it in the table. And then the resistance, same thing. As your process technology gets tighter and tighter, this equivalent resistance goes down. So in the process we're going to be playing with, it's a 0.18, so it's less than this 0.6. And you saw the resistance was, 2.6 kilo ohm micron. Okay, and as you'll see, it doesn't matter if we say it's a minimum device or a 1 micron device, because we'll be talking about ratios. Okay, let's skip that for the time being. Okay. Okay, so let's do an example here, and we come up with the estimate the delay of a fan out of one inverter. Okay, so let's work through that. The answer is 6 RC, but let's see how we get that. Okay, so what we do is, well, once you guys take a quick crack at it, I'll give you a couple minutes. See if you can try to basically replace these devices with the RC equivalent. Okay. Basically, you want to see the delay of this guy. So this first stage driving this guy, as if this is an RC combination. So what did that look like? Try to draw that circuit. Okay, so the first thing, let's draw the N-type device. Okay, again, that looks like it's a size 1, minimum size, so it's going to be R is the resistance. It'll have a switch. It'll have a capacitance, C, at the source. And then it's connected to, the source is connected to ground. The drain has a certain capacitance, C. Again, it's 1C. Because K was 1 here, okay? Now the PMOS, the drain is connected to the end, to the output. Now notice the PMOS, its width is twice the width of the N, so its capacitance is going to be 2C on the drain. okay, its resistance, it was 2R is the resistance of a minimum size, but it's going to be divided by the K, which is 2. So it's just going to be R. Whoops. Forgot to draw the switch. So it'll have a switch and it'll have a capacitance for the source going to VDD. Okay, so that's what these two guys look like. Okay, everybody see what I did there? I just replaced each one of these devices with its RC equivalent, with this RC equivalent. And then we connect that up to these guys. We just see the gate capacitance of these guys. So we'll see gate capacitance of 2C for the PMOS and 1C for the NMOS. And to get the delay, remember the delay is just RC, the prop delay. And let's see what happens here. So the capacitances, we got we got 2C, 3C, 4C, 6C. So that's going to be 6 times C. And then let's say we want the equivalent R is the same whether you're pulling up or pulling down. It's just R. Okay, so that's 6 RC is the delay. I said CR. Let's put an RC. Okay, did everybody see how I got there? Okay, so let's do the same here. Okay, so let's say we have a 3-input NAND gate. Okay, so if we want, with this model, if we want the rise and fall time to be the same, how do we size these devices? Okay, so the resistance of, if we want, the resistance of an NMOS is just R, right? But we have 3 NMOSFETs in series. So if we want this total resistance to be R, because we want the same resistance as a unit inverter, if you want this total resistance to be R, we want each one of these guys to be 3R wide, 3 times the minimum size wide. So we made them 3 times as wide. So the resistance of each one of these guys is going to be R equivalent over 3. So I'm just going to call it R over 3, sorry. R over 3, R over 3, R over 3. So here, for all these guys, K is equal to 3. They're 3 times the width of the minimum. So this total resistance, okay, is the sum, so it's just R on the pull down. On the pull up, as you know, a worst case, so now we're looking at propagation delay. So as a worst case scenario, only one of these guys is going to be on one of the pull-ups. Okay, and we want the total resistance there to also be R, so we made them 2x, 2 times the width of a nominal value. So here, for these guys, K is equal to 2. So the resistance ends up being 2R. That's the basic resistance divided by K. So that's just equal to R. So pull up is R, pull down is R. Okay, with these sizes. Okay, now basically try putting in the different capacitances that these guys will have. Why don't you guys take a minute to try to sketch that out? Okay, so let's start at the bottom here with this N MOSFET. So it's 3 times the minimum. So its source will have 3C capacitance sitting here. Because again, remember K is equal to 3 times the width. I'm going to assume that because these guys are in series, if you remember in the layout, if you really laid out this gate, we would merge the source and drains. So this is, active. These would be the polys. Okay, so these guys, because they're merged, you'd only have one capacitance for both of them, or 3C for both of them. Same with this one. Okay, here you'll have 3C for the N for this guy. And then moving up, this guy will have 2C capacitance. This guy will have 2C. This guy will have 2C here. And then the sources would also have 2C, 2C, 2C. Okay, and then the gates, this gate will have 3C. This gate will have 3C. This gate will have 3C. This gate will have 2C. This gate will have 2C, and this gate will have 2C. Okay, so if I was gonna then sum up all the capacitors, each one of these inputs will have a 2C for the P and a 3C for the N. So if I was gonna merge those, so I'm gonna add this and just call it 5C. So this and this will be 5C. And then this and this, that'll be 5C. Okay. These guys don't matter because they're all, both sides of this capacitor is hooked up to VDD on the source. Both sides of that capacitor is hooked up to VDD, same as both sides of that capacitor. It doesn't change, so we don't really care about it. Same with this guy. Both sides of that capacitor is hooked up to ground. Okay. And then we can basically add up all the capacitors on this node together. So that's 3C, 5C, 7C, 9C. So I can replace all these guys with 9C. Okay, and so we'll end up, we'll end up with basically with this equivalent. Okay. So let's stop there, guys. I know that was pretty complicated, but basically what we're doing is we're replacing for doing quick hand calculations. We're replacing the transistors, the N and the P, with something that has an equivalent resistance and an equivalent capacitance. But because we'll be adjusting the width of the N and the P's to get different noise margins and to get different speeds, we want that resistance and capacitance to scale with the width of those devices in our circuits. And that's just a very simple scaling. The wider the device, the lower the resistance and the higher the capacitance. And lastly, the basic resistance of a PMOSFET is twice the resistance we're going to use in our model, twice the resistance of basic NMOSFET. Okay. So basically all we're doing is we're trying to come up with a simple RC model for our complicated NMOS and PMOS transistors. Any questions, guys?
Not about the material, but are you gonna have like solutions out for the exam?
Yeah, I'll have that for you guys. Sorry, I'm running a little bit behind. I'll have that for you guys by this weekend.
Okay. I just really want the solution to the second one, the second problem.
By the way, the Jafar was asking about the projects. I'll have that'll out tomorrow. The question for the projects, but as a spoiler, what I'm going to ask you guys is to actually simulate the first and the second problem. And I'll have the solutions out too. But hopefully with the simulations, you'll also, see what's going
on. Professor, are we using PSpice for that?
Well, my suggestion was LTSpice. And, I put up, I don't know if I mentioned this, but I put up a tutorial on LTSpice on Blackboard. I mean, it's the link to it. I hope all you guys saw it. You're welcome to use PSpice or any spice you have access to, except, the only problem with PSpice is I use Macs and I don't have PSpice, and I haven't used PSpice for years. So I just won't be able to help you guys debug a PSpice, problem. But you're welcome to use PSpice if you like. If you wanted to use LTSpice, I believe I have this on the Blackboard. I have the sort of a sample circuit, the models for the TSMC process, et cetera, over there.
Okay, thank you, Professor.
Yeah, me and Dr. Olson, I think we're almost there. I've been trying to get Cadence enabled so students can access the Cadence tool sets, not just the PSpice, but the full set of Cadence simulation tools. But it's gone slower than we thought, so I think we're going to have to with this semester. But looks like it's going to happen, but unfortunately not for you guys. But so for this semester, I think we're just going to have to stick with just doing simulation type projects. Any other questions, guys? If not, thanks, and I'll talk to you guys on Thursday. Thanks. Bye.
Have a good one.
Take care.